Hello, everyone, and welcome to the lightning talk about the query comparison. I'm Derek from Apollo, and before we jump into the solution and how we actually achieve that, let's talk about a little bit more about the problem space. So at Apollo, my team works on Apollo Federation. So it's a great architecture building distributed graphs, right? You combine those multiple sources or GraphQL schemas into a single composed supergraph that the clients can interact with, right? It's a great architecture. Tons of companies are using it at large scales. It works, and it's pretty nice. But what makes it pretty magical is there's actually the component there at runtime which converts your client queries to the stuff that your subgraphs understand, right? So the clients sees everything at once, right? So they can select multiple fields coming from multiple places. There can be some relationship between those. So there's a query planning component that interprets this query and generates a series of steps how to, resolve that, how to communicate with your client, with your subgraphs to get this data resolved, right? And, we spent a good chunk of last year rewriting our legacy JavaScript-based query planner into a Rust native solution, right? And since in federated architecture, you got your router that's processing this for you, right? It's a critical piece of infrastructure that if that one goes down, well, you don't have any data coming back to your clients, right? So you don't have your web experiences powering up, you don't have native apps working, etc., right? So it's very critical to, what do we do over here? It should be when you upgrade your router from the JavaScript version to Rust version, your upgrade should be as seamless as possible. We don't want to break you, right? We want to ensure that it works as expected. Right, and when we were doing this, as I said, we were converting it from, we were writing that from JavaScript to Rust. And we tried to be as close as possible to the original implementation. So we followed the same algorithms, same data structures. We did also follow all the unit tests, integration tests, smoke tests, and it's all great. But it is a different language, it's a different memory model, it's a different ecosystem of libraries, and there's some small differences that arise from that, right? So when we were testing our implementation, we kind of noticed sometimes they don't match, right? And so what is the problem there? And sometimes it was very obvious, right? Like the order of fields is different, but it's the same thing, right? They're semantic equivalent. Well, for the most part, it wasn't as obvious as this, right? As your graphs grows in complexity, as your queries grows in complexities, there's actually a lot more that can be different between those two implementations. Are those two queries the same? They could be, but without looking at your schema and trying to figure out what is happening there and whether those types actually intersect with each other and they actually fulfill the same thing, it's hard to say whether they're truly the same or not, right? And furthermore, manually comparing this, hundreds of thousands of millions of operations, that simply wouldn't really scale, right? So my colleague Ducky started experimenting with ways of how we can actually automate this stuff and do it something using algorithmic approach to ensure that they are truly the same, right? Unfortunately, Ducky couldn't be here today, so I'm presenting for him, but that's a lot of stuff that he actually worked on. So he looked first at the existing work in the space, and he found out that there was a research paper from Harding in Paris that they were actually talking about how to measure the complexity of the queries and compare those to figure out which one might be costly or not. And when they were looking at it, they started that in order to compare two different queries, we have to normalize them into something that we can compare. So they followed a fairly straightforward approach, right? So we inline all the fragments, and then we replace all of our abstract selections with all the possible actual concrete type implementations, right? And this approach does work. It's just that those normalized queries can be very, very, very large, right? I've seen situations where your 100 kilobyte query can grow up into multi-megabyte string of query when you actually do that. But on the other side, things, right? If you normalize it in such a way, if both queries have the same structure, right, it means they're actually the same. So you can achieve your semantic identity there based on their structure. So we followed through with this idea and came up with another approach of doing that. So instead of looking at the normalization of the queries, that what you sent to it is the same, we wanted to compare what would be the expected response shape of your graph execution, right? But so when you execute a query, right, your server returns a data that matches your request, that has the shape, right? So the idea here is that instead of actually executing the real data, it's actually create a structure that maps to this response, and for each field that you're actually returning, just record what would we be executing in the schema itself. So you can see that, yes, we also inline the fragments for comparison there. We extract type conditions, Boolean conditions, etc. But we do it a little bit more complex form, right? So for every field, we specify what sort of a concrete type it can be at runtime. We record the conditions that this is, select this was true, where it's false. We calculate, we capture all the arguments, directives, all that stuff into this form. And if we normalize it like this, we can actually also compare them fairly efficiently. But your normalized responses, they might still be slightly different. So one subgraph may say, I have a inline fragment selection on some interface, and then I narrow it down to just implementation type, and I select a field, right? Another one may say, well, I'm just going to be selecting on that specific type, right? So technically, those two are semantically correct, but if you want to compare those two directly, it's actually not that straightforward. So instead, we can perform a subset test, saying if response of our query A is a subset of another one, we know that if we flip it around based on the sets, if the query B is a subset of query A and A is a subset of query B, it means that they have to be equivalent to each other. And they're equivalent if for every single entry in our response, there's going to be the same in both of the response shapes, right? So based on following on this, we can achieve the semantic equivalence as well. And to summarize this is a fairly practical technique that you can use for comparison of GraphQL queries. Interestingly enough, GraphQL spec is, well, sometimes ambiguous in certain cases. So like it doesn't really deal with custom directives. And since you can select field multiple times and they can have different directives, it doesn't really tell you how it's going to happen. So it's up to your server implementation. So we chose one approach or not. And what's interesting is that this approach, well, we extended it also to verify the correctness of our query plans, right? So yes, you have a unit test and all the stuff that you verified that, okay, given these inputs, I expect this query, right? But how do you know that your algorithm is actually correct? Because when you call the query planner, you get your original client query, right? Then we process it, we normalize it, we start generating those different fetches for the subgraphs. They might be adding additional data there, like for all the required fields, all the dependencies. So how do you know that whatever you generated, it actually is going to fulfill the needs of your original query? So using this approach and following the subset test, we can say if you sum up all your responses and generate a final response shape of all of those subgraph fetches, we can see that if original query is passing the subset test, it means that whatever we generated is guaranteed to actually be valid response for the clients. And last but not least, well, you can try it out yourself. It is actually open source and available on our GitHub repo. So you can go ahead and play around with it. So thanks. I think we might have a couple minutes for questions if folks have any questions. Sure.
I'm trying to understand how this is doing. So when you analyze the response, it means you have to execute both your original query and any query you're comparing.
Yes, you have to normalize it first, yes.
So if it's used for query planning, you cannot use it for the planning of the original query because you have to execute the query.
Well, you can normalize your input query, right? And you have outputs of it, so you can also normalize the outputs. So your original stuff or query can be compared to the outputs as well. But well, you have to. Well, if you already went through the normalization process and you don't have a hold of your original query, then yes. Well, you have to be able to have two things to compare, right? But go.
Have you found other use cases than testing that query plans or queries are equivalent for this? Like, for example, I think maybe analytics would be like if you want to treat different queries for metrics purposes the same, or that sort of other use cases?
Well, so we use that to ensure that, well, our Bolt implementation produced semantically equivalent queries, right? So that was a very strong need for us to do that. And the query plan correctness check was kind of like a bonus after that. But technically, yeah, there could be some additional use cases that could be done based on that.
Sounds like a very cool tool.
Yes. The gentleman in the back that I never seen in my life.
Do you know of any correlation between how similar the normalized query is and the original query document and the actual text of the document received? Is there any correlation between like how similar those are? That is to say, like a document that might have been super compact and then on normalization is quite large, like you talked about, and the amount of complexity it would take to execute it, I guess, at runtime. Are you aware of any like kind of correlation there?
I don't have that statistics on top of my head, but I've seen the queries that, if you're using nested fragments, they can grow to multi-megabyte strings. So then comparing those multi-megabyte queries is going to be probably much more resource intensive than comparing a subset of it that clients expect. But yes, the larger the query, it's going to take a little bit longer to normalize also and compare it. Good. Well, thanks, everyone.